The primary objective of modern engineering is the creation of autonomous systems capable of sensing, deciding, and acting within uncertain environments. Mechatronics defines the systems engineering mindset required to build them. It mandates that mechanical, electronic, and software subsystems are conceived and optimized as a single, interdependent entity from the earliest design stages. Historically, engineering domains matured independently, with mechanical design focused strictly on physical strength. In the mid-20th century, electrical integration simply meant attaching motors to existing assemblies, without true cross-domain coordination. Today, embedded computation and artificial intelligence are tightly coupled with moving physical processes. Because the software and the hardware are deeply intertwined, achieving optimal performance in a cyber-physical system is mathematically and physically impossible using isolated component-level optimization. This diagram illustrates the traditional sequential engineering workflow. Mechanical engineers lock in a physical chassis before passing the design to electrical teams, who eventually hand the wired hardware to software developers. That linear approach fails when applied to modern complexity. A design choice made in one domain instantly and permanently restricts the operational limits of every other subsystem. If mechanical engineers optimize a chassis for structural integrity by adding mass, they increase the current required by the motors. That extra power draw can cause voltage drops that disrupt the embedded controller, making it impossible for the software to meet its real-time processing requirements. The results are endless redesign cycles, integration conflicts during the assembly phase, and compromised system performance that often goes undetected until late in development. To manage the compounding complexity of smart machines, engineering teams must replace sequential workflows with concurrent systems engineering. This Venn diagram identifies the intersection of four distinct branches of engineering. Mechatronics acts as the central coordinating hub between mechanical, electrical, control, and computer systems. This diagram translates conceptual overlap into physical architecture. Mechanical and electrical subsystems provide the foundation for actuation, while software and control subsystems form the computational layer. Interface arrows reveal cascading constraints. Increasing mechanical load requires a larger motor, generating heat that limits the control processor's speed. Because these domains are inextricably linked, the engineering focus must shift from the optimization of individual parts to the precise management of their interactions. This creates a logistical problem. If every component choice affects every other domain, how does a team draft a system architecture without creating immediate conflicts? Engineers solve this through functional decomposition. Instead of organizing a project by physical parts, they organize the design effort by required actions. The process involves taking a high-level system requirement and slicing it into smaller, manageable subfunctions spanning multiple disciplines. Motion control is mapped across 3 domains simultaneously, requiring mechanical actuation, electronic position sensing, and software logic to process commands. Functional decomposition prevents isolated design by forcing interdisciplinary teams to collaborate on shared performance goals before any hardware is manufactured. This graphic outlines the V-model lifecycle. The downward left slope represents the design phase, moving from abstract requirements into granular specifications. The upward right slope represents integration, combining code and hardware against those specs. Traceability links ensure every right-side physical test validates a left-side requirement. At the base of the V-model, engineers utilize hardware-software co-design. This allows mechanical and electronic iterations to happen in parallel rather than waiting for physical prototypes. Teams use digital twins and virtual simulation environments during this phase to catch integration errors. These digital models allow for thousands of test cycles before a single physical component is produced. The V-model is a rigorous necessity. It provides the structured path to ensure that life-critical mechatronic systems behave exactly as intended under real-world conditions. This table identifies the trade-offs of the mechatronic approach. Concurrent engineering significantly increases upfront system complexity and requires a high level of specialized interdisciplinary expertise, which drives up initial development costs. Coupling physical hardware with software also introduces specific vulnerabilities, such as susceptibility to electromagnetic interference, software bugs, and potential cyber threats. These risks are balanced by the advantages. Digital control and modular software architectures allow for a level of precision, rapid iteration, and hardware flexibility that purely mechanical systems cannot provide. While the upfront cost of an integrated approach is high, ignoring these interdependencies guarantees failure in any industry requiring smart, adaptive technology. When software physically interacts with humans or hazardous environments, safety and reliability are not secondary features. They are the primary design requirements. This landscape illustrates how the systems mindset supports the most critical advancements of our era, from smart energy grids and automated factories to advanced medical robotics. The next trajectory involves the convergence of distributed mechatronic platforms with global communication networks, pushing toward large-scale autonomous infrastructure. Mechatronics is the foundational language of modern engineering. It provides the architectural framework necessary to translate high-level artificial intelligence into precise, real-world physical action.